Hello, everyone. My name is Jerry Gu. I'm a PhD student at Northeastern University, and today I'll be giving a tutorial on generating metadata with HDF5 for the rfdatafactory project. In this tutorial, we'll be covering what is metadata, what is HDF5, what our code implements in regards to HDF5, and an example of metadata generation with HDF5. So first of all, what is metadata? Metadata is any descriptive information about sensors and equipment, experiments in general, or data sets in general. As an example, here's a snapshot of our flash data set, which in brief is a multimodal data set obtained through a millimeter wave beam selection in vehicular networks. So using metadata, we can describe anything such as the sensors being used, such as the GoPro Hero 4 camera or the Talon 80-7200 router, the experiment in general, for example, what scenario we're collecting or what environment we're collecting the experiment in, and the data set in general. So for example, where the data is stored or what is done to the data, such as synchronization of these separate data files. In short, metadata is data about data. Now, what is HDF5? The hierarchical data format 5, HDF5, is a package for data management and storage, which has the following features. It is a versatile data model that can represent very complex data objects, along with their corresponding metadata. It is a portable file format with no size limit or data object limit. It is a software library that runs on a wide range of platforms and implements a variety of APIs such as C, C++, and Java. It also has third-party bindings in Python and MATLAB, among other libraries. It is a rich set of integrated performance features that allow for time and storage optimizations. And it is a set of tools and applications for managing, manipulating, and viewing data or data sets. So why should we use HDF5? HDF5 has features that are found in many other data formats, such as the XML format, which allow users to create self-describing files that describe the relationship between the data, and the PDF format, which can contain, in which the HDF5 file can contain heterogeneous information. However, HDF5 has more capabilities. It can contain binary data in any sort of representation, and it can allow the user to access parts of a file or data set without the need to analyze or open the entire file. HDF5 contains two primary objects, one being groups. So think of a group as a folder. It's a structure containing 0 or more HDF5 objects, and groups may contain other groups. And of course, it can contain a data set, which is represented as an array of data elements. So any group or data set within HDF5 may have an attribute list, and this is where the metadata comes into play. So for example, if I were to implement HDF5 in Python, here is a sample implementation of the Flash data set. I'm using the H5 library to implement HDF5. I can very easily write a HDF5 file, generate groups, generate subgroups within this larger group, and insert a data set within the subgroup. So in this case, I'm inserting a set of GPS coordinates in this larger group. So for the rfdatafactory project, our implementation is very simple. We use two simple codes, one being generate HDF5 dataset, to generate the HDF5 file, and the other one being read HDF5 to read the generated HDF5 file. There are also only two shell scripts that are used to run these codes, one being run_generate and the other being run_read, and to run the respective Python codes. And in order to run these two shell scripts, you only need to change a few attributes, one being in run_generate, the destination directory, the source directory, the file path to the metadata, and the file name of the HDF5 file that you want to create. And in the run_read shell script, you'll need to change the path to the HDF5 file. So as a brief example of what this looks like in the rfdatafactory repository, I'll briefly open the HDF5 folder, show you the path. I'll show you what the generate HDF5 dataset looks like. So again, this uses the H5 library. It can create subgroups. So in this specific example, we're making subgroups for each sensor used in the Flash dataset. It can detect metadata from an existing metadata file and write that metadata to the HDF5 file. And it can store the entire dataset in that same HDF5 file. In the read HDF5 dataset, again, it's a very similar process using the H5 library. It will detect the subgroups within the generated HDF5 file and print them out. And it will give you both, in this example, data and any relevant metadata that is stored in the HDF5 file. Now back to the presentation. So as an example, using the aforementioned codes, to run the shell scripts, I've changed the following features. In the run_generate shell script, I've changed the paths to the source and destination files, as well as created a test dummy HDF5 file to store everything in. And I've also specified this path to the shell script where the HDF5 file will be. And showing you what it looks like when you run the programs, when you run run_generate, should have a clean output. And when you run_read, it will give you the appropriate or detected attributes and data. So for example, we have here the metadata in the forms of the detected sensors, as well as any other distinguishing features about the experiment being recorded. And we have some of the data itself. So in this specific example, again, we're showing you the generated or the recorded GPS coordinates. So that's it for this tutorial. If you want to check out the Data Factory repository, here's the link. If you want to know more about the Flash dataset, you can check out our paper on the Flash dataset. And if you'd like to contact us, feel free to send us an email at any one of these 3 emails. Thank you.